In this problem, I want to get the limit of an infinite sequence that's given by this rational function. And this goes back to some limits that were very common in Calculus 1. I just want the large n limit of this, so the limit as n goes to infinity of this rational function 2 minus n cubed over 2n cubed plus n squared minus 5. And there's an informal way to handle this, and there's a formal way to handle this. And I want to illustrate the informal way first. So what you do is you make this argument that if n is extremely large, then higher powers of n are going to dominate in any sum or difference that appears in the problem. So like n cubed, if you imagine n was 1,000,000 or 10 to the 6th, n cubed is going to be like 10 to the 18th. And then there's this puny little constant over here that's going to be making a correction 18 decimal places later. So this is sort of an approximation approach. I would say that numerator to a very good percentage approximation is just negative n cubed. And you make the same argument down in the denominator. It's not as dramatic, but if n was 1,000,000, for example, n cubed would be 10 to the 18th, n squared would be 10 to the 12th. That's a correction 6 decimal places later, and the constant is even less significant than that. So to a very good approximation, as a percentage, that denominator is going to be close to 3n cubed. Now I can cancel those n cubes. And this is just the limit as n goes to infinity of negative 1/3, which is just negative 1/3. So the terms of this sequence are settling down and approaching negative 1/3 when n becomes large. There's a slightly more formal approach to this that you could take. And I think a lot of teachers require this in calculus, so I should illustrate how it goes. You can divide the top and bottom of this thing by the highest power of n. Hopefully that rings a bell. This is something that you should have done in Calc 1. So in the numerator, I get 2 over n cubed minus 1. In the denominator, I get 3 plus 1 over n minus 5 over n cubed. And the assumption here is that at some point earlier in your coursework, you've proven that all of these limits go to 0 as n becomes large. But in practice, this is really just a semi-formal approach to the problem, because you normally don't do a rigorous proof that each of these things goes to 0. You just kind of state it as a theorem that's not formally proven usually. So it's still not 100% formal, but it's slightly more formal. The limit of a fraction is the fraction of the limits. Limits distribute across sums and differences. And so I can take the limit of every single one of these terms, and then all the ones with n's in the denominator are 0, and the only survivors here are the negative 1 in the numerator and the 3 in the denominator. So I end up with the same answer.